Imagine a computer so powerful that it could solve problems in minutes, problems that would take classical computers billions of years to crack. This is not science fiction. This is the promise of quantum computing, a revolutionary technology harnessing the strange and fascinating laws of quantum mechanics. Quantum computing has the potential to transform fields like medicine, materials science, and artificial intelligence, making what once seemed impossible, possible. Imagine designing life-saving drugs at a fraction of the time it takes today, or creating materials with properties we've only dreamed of. Classical computers use bits, which can be either a 0 or a 1, to store information. This binary system has been the foundation of computing for decades. Quantum computers, however, employ qubits. Unlike classical bits, qubits can exist in a state of superposition, allowing them to be both 0 and 1 simultaneously. This principle of superposition enables quantum computers to process and store information in a fundamentally different way, leading to exponential speedups for certain types of calculations. The implications of this technology are staggering. We could solve complex problems that are currently beyond our reach, revolutionizing industries and scientific research. We could design life-saving drugs, create unbreakable encryption, and develop new materials with unprecedented properties. The potential applications are vast and varied, limited only by our imagination and ingenuity. However, this potential comes with significant challenges. Building and operating a quantum computer is like trying to build a house of cards in the middle of a hurricane. The very nature of quantum mechanics that gives these machines their power also makes them incredibly fragile and prone to errors. Even the slightest disturbance can cause a quantum computer to lose its delicate state. Researchers are working tirelessly to develop error correction techniques and stabilize these systems, but it remains a daunting task. Overcoming these challenges is crucial for unlocking the full potential of quantum computing and ushering in a new era of technological advancement. The future is quantum, and it promises to be extraordinary. At the heart of every quantum computer lie qubits, the quantum equivalent of bits in classical computing. These qubits are the fundamental building blocks that enable quantum computers to perform complex calculations at unprecedented speeds. Unlike bits, which can be either a 0 or a 1, qubits can exist in a superposition. This unique property allows them to be in multiple states at once, providing a significant advantage over classical bits. This means they can be in both states simultaneously, vastly increasing their computational power. The ability to process multiple possibilities at once is what makes quantum computing so powerful and revolutionary. Imagine a coin spinning in the air, not yet settled as heads or tails. That's the essence of superposition. This analogy helps to visualize how qubits can hold multiple states at the same time. However, this delicate state is extremely vulnerable to disturbances from the surrounding environment. Even the slightest interference can cause significant issues. The slightest vibration, change in temperature, or even stray electromagnetic fields can disrupt a qubit's superposition, leading to errors in calculations. These disturbances can cause the qubits to lose their quantum state, resulting in computational inaccuracies. This phenomenon, known as decoherence, is one of the biggest hurdles in quantum computing. Decoherence makes it difficult to maintain the integrity of qubits over time. Imagine trying to balance a pencil on its tip. The slightest disturbance can cause it to fall. The slightest breeze or vibration will cause it to topple. Similarly, qubits are highly sensitive to their surroundings, making them prone to errors. Similarly, qubits are highly sensitive to their surroundings. This sensitivity requires extremely controlled environments to function correctly. This sensitivity makes it extremely challenging to maintain their quantum properties for extended periods, limiting the complexity and reliability of quantum computations. Researchers are continuously working on methods to stabilize qubits and reduce the impact of decoherence, aiming to unlock the full potential of quantum computing. In the classical computing world, error correction is relatively straightforward. Errors are detected and corrected by copying and comparing data. Data is typically copied and compared to detect and correct errors. This process ensures that any discrepancies can be identified and fixed promptly. However, the very act of measuring a qubit's state causes it to collapse out of superposition, destroying the quantum information it holds. This unique challenge makes error correction in quantum computing a far more delicate and complex affair. Scientists have to be extremely careful and innovative to address this issue. They have developed ingenious techniques that indirectly detect and correct errors without directly measuring the qubits themselves. To address this, scientists have developed ingenious techniques that indirectly detect and correct errors without directly measuring the qubits themselves. These methods are crucial for maintaining the integrity of quantum information. One such method involves using multiple physical qubits to encode a single logical qubit. This redundancy allows for the detection and correction of errors on the physical qubits. Preserving the integrity of the logical qubit and the information it carries. It's like having multiple backups for a single piece of data. Imagine a group of dancers moving in unison, representing a single piece of information. Each dancer's movement is crucial to the overall performance. If one dancer makes a mistake, the others can compensate, ensuring the overall performance remains intact. This analogy helps to understand how multiple qubits work together. Similarly, multiple physical qubits work together to protect the logical qubit from errors. This collaborative effort is essential for the stability and reliability of quantum computing systems. Building a quantum computer with a handful of qubits is hard enough, but scaling up to the thousands or even millions needed for practical applications presents a monumental engineering challenge. Each qubit needs to be precisely controlled and isolated from its environment to minimize decoherence. This often requires maintaining temperatures close to absolute zero, colder than the depths of outer space. Moreover, as the number of qubits increases, so does the complexity of their interactions. Managing these interactions while preventing unwanted entanglement, where qubits become correlated in unpredictable ways, is crucial for reliable computations. It's like trying to orchestrate a symphony of extremely sensitive instruments, each susceptible to the slightest disturbance. Section 5. Bridging the gap: hybrid systems in quantum computing. As researchers continue to grapple with the challenges of building large-scale, fault-tolerant quantum computers, a promising interim solution has emerged: hybrid systems. These systems combine the unique capabilities of quantum computers with the established power of classical computers. The idea is to leverage the strengths of both worlds to tackle complex problems. In a hybrid system, a classical computer acts as the conductor, handling the bulk of the computation and delegating specific tasks that require the unique capabilities of quantum mechanics to a smaller, specialized quantum processor. This approach circumvents the limitations of current quantum hardware while still harnessing its potential advantages. Imagine a construction project where a team of robots performs the heavy lifting, and a human architect oversees the design and makes critical decisions. Similarly, hybrid systems combine the raw processing power of classical computers with the specialized skills of quantum processors. Section 6. The quest for stability: conquering decoherence. Decoherence, the Achilles heel of quantum computing, arises from the unavoidable interaction between a qubit and its surroundings. Even the slightest environmental disturbance can disrupt a qubit's delicate quantum state, leading to errors. Overcoming decoherence is paramount to building stable and reliable quantum computers. Scientists are exploring various approaches to mitigate decoherence. One strategy involves developing more robust qubits that are less susceptible to environmental noise. Another focuses on designing sophisticated error correction codes that can detect and correct errors as they occur. Additionally, researchers are investigating ways to create more controlled environments for qubits, shielding them from external disturbances. Section 7. A future entangled quantum computing's potential. The challenges in quantum computing are undoubtedly immense, but so are the potential rewards. Imagine a world where we can design new materials atom by atom, revolutionizing industries from energy to manufacturing. Picture developing personalized medicine tailored to an individual's genetic makeup, leading to more effective treatments and cures. Quantum computers could break the encryption that protects our online data, demanding a complete overhaul of cybersecurity. They could also supercharge artificial intelligence, enabling machines to learn and solve problems at unprecedented speeds. The possibilities, like the quantum world itself, are both exciting and uncharted. Section 8. The power of collaboration: advancing quantum research. The quest to build practical quantum computers is a global endeavor. Researchers from academia, industry, and government institutions are collaborating like never before, sharing knowledge and resources to overcome the formidable challenges. This spirit of collaboration is crucial for driving innovation and accelerating progress in this rapidly evolving field. Open-source platforms and initiatives are fostering a vibrant community of quantum enthusiasts, from students to seasoned professionals. This collaborative environment is essential for nurturing new ideas, developing talent, and ensuring that the benefits of quantum computing are shared widely. Section 9. At the cusp of a new era. Quantum computing stands at the cusp of a new era in technological advancement. While significant challenges remain in achieving the full potential of this revolutionary technology, the progress made in recent years is nothing short of remarkable. As research continues to unravel the mysteries of the quantum world, we are moving closer to a future where quantum computers will transform our world in ways we can only begin to imagine. The journey ahead is challenging but also incredibly exciting. By pushing the boundaries of science and engineering, we are not only unlocking the secrets of the universe but also shaping the future of technology and our place within it.